Today's speaker is Professor Jason Ho from North Carolina State University. Jason's talk will be on sensitivity and uncertainty analysis. How can we learn from them to achieve better designs of advanced reactors? Jason holds a PhD and Master of Science degrees from Pennsylvania State University and University of Michigan, and he's previously been at University of California, Berkeley, and Tsinghua University in China as well. And he has been doing some really interesting work on uncertainty quantification of light water reactors and advanced reactors such as sodium fast reactors over the past few years, and how these, and has worked on validating these models on experimental facilities as well. He also coordinates the OECD NEA time-dependent neutron transport benchmark. So it's really great to have you here today, Jason. Over to you.
All right, Ben, thank you for the introduction. Hello, everyone. I'm Jason Ho. I'm assistant professor of nuclear engineering at North Carolina State University. I'm very glad to be here and to give you this talk on sensitivity and uncertainty analysis and how we can use them to advance the advanced reactor design and analysis. So before I get started, I'll first briefly introduce our university and our program. This is our mascot, Wolfpack. Our program, in a glance, is actually the first nuclear engineering curriculum and university reactor in the US. So this year we're celebrating our 7th anniversary of our program and the 60th anniversary of our Department of Nuclear Engineering. So in the past 3 years, we have been ranked number 3 in the nuclear engineering graduate programs. And this is done by the US News and World Report. And we're also one of the best, we have one of the best online master program of nuclear engineering. And right at the moment, we have 23 tenure and tenure track faculty. And we also have 3 research professors, and some of them their photos are shown here on the right. And we also have the joint faculty appointments with various national labs. And last year, the last academic year, we have graduated 23 PhDs. That's what we're really proud of. Recently, there has been some development in the program. We're a member of the 2 awarded US DOE Advanced Reactor Development Program, ARDP projects, one with X Energy, one with Tire Power, and GE Hitachi. We're working with those companies, designing and, more importantly, building the advanced reactors in the next 7 years. And we also partner in the US DOE funded Center for Low Temperature Plasma Interactions with Complex Interfaces. We're also partner in the 11 University DOE funded Nuclear Science and Security Consortium. At the moment, we're constructing a number of research facilities, fission gas loop, hot cell facility, and ultra cold neutron source. And on the curriculum side, we're developing the undergraduate concentration in plasma science and engineering and nuclear materials. Also, the graduate certificate in health physics, nuclear reactor engineering, and graduate concentrations in plasma science, engineering, and nuclear materials. So also, a little bit about our state. I'm not sure how many of you have visited North Carolina, which is a beautiful place to live in. Our university is located in the capital of the state, Raleigh, and we're 2 hours away from a mountain, Great Smoky Mountain to the west, and also 2 hours away from the Pacific Ocean, Atlantic to the east. And then actually, North Carolina is a nuclear state, and 32% of the electricity comes from nuclear power. And at Charlotte, we have an energy hub. GE Hitachi is headquartered in the Wilmington area, and Duke Energy is headquartered in Charlotte. So give us a visit, the university and also North Carolina. We have a chance, when, of course, when the pandemic is over, it's definitely worth a visit. And also just a couple of words about the research group I work in. This is called the Reactor Dynamics and Fuel Modeling Group. It is the largest research group in our department. We have 3 faculty members, Dr. Avramova, Dr. Ivanov, and myself. We have also senior research scholar and a few postdoc scholars. We have 20 plus graduate students. So the way we found, we work together is that most of us work on the multi-physics modeling simulation reactor systems. Someone working in one specific area, and so all of us work all together naturally, and the nature of our work make this collaboration really, really easy. And if you want to learn more about research, please go to this website and to check for more details. So let's get to the main topic of this seminar. We'll talk about sensitivity and uncertainty analysis in modeling and how we apply them to the advanced reactor design and analysis. So we need to first just to clarify a few things. For example, what do you mean by sensitivity and what do you mean by uncertainty, right? So starting point is that a mathematical model contains certain parameters and also the response dependent on this model. So by performing sensitivity analysis, the answer we're trying to find, the question we're trying to answer is, if one of the parameters is perturbed, right, how will this affect the response? And the way we do it is that we can compute the derivatives of the response with respect to all the parameters of interest. The easiest way or simplest case would be just to calculate the local sensitivity of the response R with respect to the parameter alpha at certain condition alpha 0. And this equation is simply this ratio of the relative change of the response to the relative change of the input parameter. On the other hand, we have uncertainty analysis, where we really want to compute the probability distribution of the response based on the probability distribution of the uncertain parameters. So this is really how you propagate the uncertainty from the input or the modeling parameter to the response or the quantity of interest. Usually it's difficult to determine the exact distribution of the response. So often what we do is to compute only the variance or covariances of the parameter, or we estimate the distribution based on simulations. So why is this important for advanced reactors? Because advanced reactors has usually suffers from the limited operational history compared with the light water reactors. Over the years, we did have some advanced reactors built and operated, but there's nothing comparable with light water reactors. So if we really want to advance advanced reactor technology, the first thing we need to rely on is the advanced modeling and simulation capabilities. And then the uncertainty propagation is important in the sense that we can really understand the impact of the uncertainty of the input variables to the system responses under steady state and transient conditions. One application area is basically the so-called bedpool application, the best estimate plus uncertainty. So where you can really combine the best estimate code and or tools and data, and with the quantified uncertainty from the input and modeling parameters. So on top of this best estimated value calculated by the best estimate tools and using the data, you add this uncertainty on top of it so that you can have a more realistic estimate of your, for example, safety margin compared with the previous adopted approach, which is conservatism. But what we're trying to talk today is not this. We're trying to think or trying to talk about how we can use the sensitivity and uncertainty in the design optimization and the validation of numerical tools. All right, so in the first part, we are really trying to find out the best combination of design parameters for certain advanced reactors. The second topic, we're really trying to understand the deviation that we observed of the calculated or predicted value from numerical tools from the measurement data. Okay, so I'm going to divide the talk into two parts. The first one, we will talk about the advanced reactor design optimization. And the second part is about the safety analysis model validation. And in addition to sensitivity, and then certainly we'll touch a few different concepts for example, the optimization algorithms, reduced order modeling, and experimental measurements. You will see a lot of computer codes in this presentation, but don't be overwhelmed by that. Keep in mind the method I'm going to show you and the code I'm going to mention, or the method I'm going to show you are really reactor and code agnostic. Okay, so they can be applied to other reactor types, and those computer codes can be replaced with other codes in different conditions. Not to say that those codes are not important, they are, but that's not the main focus of this talk. So we get to the first part, which is the design optimization. This is a work we did a couple of years ago in collaboration with Argonne National Lab and Sandia National Labs. These are the people who have contributed to this work, and at the bottom we have a publication. If you're interested, please check it out. So this work is about the optimization of the so-called advanced burner test reactor. You can tell it's a test reactor which is used to demonstrate the benefit of transportation technologies and the closed fuel cycle. It's a sodium-cooled fast reactor. It's fueled with a metal alloy fuel, uranium, transuranics, and zirconium. Okay, it has a look that is typical to any sodium-cooled fast reactor using the hexagonal fuel bundle or fuel assembly design, and it has the inner core and outer core and the reflector and shield region, and then you have this different control assemblies scattered across the active core. The table over here shows a reference design from a previous study. So that is a starting point. There are a few things we want to do to optimize the design. By optimize, I mean really improving the performance. We want to look at a few things: reactivity swing, core power, core volume, external plutonium field every year, and the peak fast flux. We look at those parameters for various reasons. For the reactivity swing, we're really trying to make sure that we have enough shutdown margin for the fast reactor, right? And make sure that there's not, our control worth is large enough to cover the reactivity swing. For the core power and volume, it really is it's related to the construction cost of this reactor. And for the external fuel, plutonium feed, that is about related to the fuel costs every year. And the peak fast flux is related to the irradiation environment in the reactor. After all, this is a test reactor. You're going to test some materials in the reactor. So in the end, we want to optimize this reactor by reducing the first four parameters and maximizing the last one, the peak fast flux. So that's our high level overview of our optimization objectives. So what can we do to achieve those goals? And what are the things we are allowed to play with? On the left, I list a few design parameters. For example, the height of the active driver fuel, the radius of the inner cladding surface, the radius of the wire wrap structure, number of rings of pins per assembly, number of inner core batches, and of course the cycle length. So these are the things we can play with to maximize or minimize the objectives listed on the right. And this is a tricky problem because you can tell some of the design objectives are conflicting with each other. For example, if you want to minimize the reactor core power, you can't really maximize the peak fast flux. These are closely related, are correlated. So you can't really reduce one by increasing the other one. So that's what we call a trade-off, right? On the left, you have the X, which is the design parameters. And this blue box design define the design space you have. You can move inside the space. On the right, you have projected performance, which is, a function of different responses, R1 and R2. You have 5 over here. And like I said, there's always a trade-off between those parameters. So in the end, you can't really, if this is a minimization problem, you can't really reach to this point, meaning that you can't really minimizing one without increasing the other one. So in the end, you would expect you have some solutions along this line, which is called Pareto front, and then you can choose from those set of solutions in the end. But what makes it more complicated is that we not only have those design objectives, we also have a list of design constraints. So these are the parameters that we don't want to violate. Some of them are safety related, some of them are economic related. For example, there is cladding temperature, the fuel temperature. This is obviously safety related. And there's discharge burnup. This is economic related. So there are different things that you need to put in your into your consideration as you perform the optimization. And the first thing you need to do is really to refine your optimization problems. You look at your input variables and you have to discretize the input variables if they're continuous. For example, the height of the driver fuel, the radius, these are continuous variable by nature, but you have to discretize it. Otherwise, you won't be able to perform this type of, optimization. So this table shows how we discretize things and how many number of samples do we get for each of the input parameters. And by combining everything together, you reach to a huge design space. We're talking about more than 11 billion designs or the combination of design parameters. Apparently, you can't really exhaust all those permutations. You need an optimization algorithm, which we'll talk in a minute. And next, how are you going to evaluate the performance? You have a design, which is basically a set of design parameters, and you need some computational tool to tell you, okay, what is performance of this? What is the reactivity swing? What is the core volume, etc. And here we use the so-called argon reactor computation code suite ARC implemented with on the NIMS workbench. So don't worry about too much about those codes. Just very quickly, I'll tell you what they do. So first, you generate cross sections, fine group structure cross sections, and you feed them into this Rebus, this core, the cycle calculation. In Rebus, there is a code called diff3d, which is a nodal transport code. It solves the transport equation in the nodal representation. And then this is basically where you got the core performance parameters. And then you perform a sensitivity, the percent calculation, which is a sensitivity-based calculation where you get kinetics parameters, you get the feedback coefficients. Then you perform a simple TH calculation, and then you call it a day. That's the end of the calculation. You can see that the whole calculation sequence takes about 13, 14 minutes, and that's, it's short compared with the high fidelity codes, but still long if you want to perform optimization problem where you have to look into tens of, thousands of designs. So it's really time consuming. So in the end, we probably need some type of acceleration technique, which we look into the circuit model, which I'll talk later. So, okay, so when you have defined your optimization problem, you look at your computational tools available to you, and next thing you're considering is really, can we simplify this problem a little bit? By simplifying, I mean, can we reduce the number of input and output? There's just so many of them, and it's really difficult to handle. So that's where the sensitivity analysis becomes handy. We're trying to establish, again, this relationship between the output quantity, which is all those objective functions, and the input parameters, which are listed here. So we perform this global sensitivity analysis, and we calculate the so-called Pearson coefficients, which really tells the linear dependence of the input and output, and among also the output parameters as well. So this is a very busy table, but basically the left part here shows the correlation between the output and the input parameters. Over here, this black box shows the correlations between the objective parameters, or these are the 5 of them. So one thing you can notice that is that some of the input parameters are probably not so important to most of the design objectives. For example, the wear right radius. It doesn't really have much impact on the objectives. As you can see that those numbers are very small. By the way, the Pearson coefficients has a value range from -1 to 1. -1 being negatively correlated, linearly correlated, and 1 being positively and linearly correlated. If you have a number close to 0, it means the correlation between these two variables are very small. So you can see that this guy doesn't really have large of impact on the design and the performance of the design. On the other hand, if you look at the objective space or the response space, okay, and you notice that some of them, for example, this is reactivity swing, is highly correlated to almost all of them, all the rest, right? You have this large numbers, whether it's positive or negative, they're large. It means, okay, reactivity swings probably can be represented by the rest of the design objectives. You don't have to also include that. And the same applies to the core volume. So in the end, we decided, based on the sensitivity analysis, we decided to remove the core volume and reactivity swing from the objectives so that the problem becomes more easier to handle. And we also reduce some of the input parameter on the left-hand side. So now you have defined and refined your optimization problem, and next you will choose a optimization method. And then after you have the optimization method, you can start doing the optimization. But one thing we need to look at is really how can you accelerate your optimization? Because again, your computational tool is still very expensive. You need to have a tool that runs faster and give you the, but still give you the, relatively speaking, accurate results. So the optimization method we pick for the study is the genetic algorithm. Many of you have probably heard about it or even used it before. So the idea is from the natural selection. Basically, the individual that has the highest fitness values will survive and be reproduced to the next generation. So if you consider at the beginning, you have 5 cases, just for demonstration purpose. You have 5 cases or 5 designs. And, and then you rank them by certain attributes. For example, the core power. You rank them from the highest to the lowest. And you want save the top 3, let's say, to that and pass it to the next generation because they are best performing among all the cases. But you also want to create, diversity in your generation. What you do is that you pick the two best performing individuals, and you mate them, right? And you pick the design parameters associated with the two cases, in this case 5 and 3, and you reproduce them in their child, right? And so you pick the blue bar from the first one, you pick the orange bar from the second one. What you also can do is you can create a mutation by just randomly change some of the parameters, design parameters in the solution, so that you create a new individual or a new solution in that case, and you pass it to the next generation. Again, I'm oversimplifying this whole process, but the idea is you pick the best performing individuals, you take their genes if you want, and pass it to the next generation. And so that you can always looking for better solutions. But at the same time, you're creating mutations to introduce variations or diversity into their generation, so that you don't be stuck in the local, optimal, so that it gives you the ability to explore the design space a little bit. All right. So the way we do it, the way we implement it is that we use Dakota as the driver to drive the whole mechanism, right? Dakota is a code from San Diego National Lab. You use Dakota to sample your input parameters. By sampling, I mean you perturb your input parameters within the range that you define earlier. Then you have a whole bunch of sample cases. These are the different designs. And you proceed with ARC. You use ARC to calculate the core responses, etc. And then you collect all the results, you process it, and then you go to feed it back to the optimization algorithm. The optimization algorithm, which is generic algorithm, will tell you which new solutions you should be looking at through this, selection. Then you go to the next generation, you repeat until you reach whatever design objectives that you define to begin with. So some example results. So we first tested the ARC-based optimization uses multi-objective genetic algorithm. It's multi-objective because we have multiple objectives. In this case, we have 3 of them. Remember that we took 2, we crossed 2 off at the beginning of this process. Okay, in the end, this is the mechanism, right? So you use ARC. So basically, you generate different solutions and use ARC to evaluate it. Again, ARC is very expensive, but this is first attempt. And then you feed it back to the genetic algorithm, which tells you which new solutions you should be looking at in the next generation. And then you go back to ARC, evaluate those, and you iterate between the algorithm and the ARC system. So let me see, how can I play this here? So here I'm showing you the solution, which is represented by those dots, and their relationship with their performance. The 3 parameters x, y, and z create a 3D space of these 3 design objectives: the plutonium external feed, the core power, and peak fast flux. Remember, we want to have highest peak fast flux as possible. We want the core power to be low, and we want the plutonium external feed to be low. So in the end, in this 3D space, we'll be looking for results in this area, okay? So as we simulate and generate more solutions each generation, so every time you see a whole bunch of dots being added to the plot, it means a new generation is being added and evaluated. So the color changes over generation. You see that at the beginning, there is dots scattered across the entire space, but overall, over time, you can see that color is being concentrated along this curve. That means we're able to really find the Pareto front that satisfy our design objectives. right? So from the beginning to the end, which is yellow, you can see that more and more solutions are being generated in this curve. That means this algorithm is actually working. So if you project the three-dimensional plot into, again, into 2D spaces, the three 2D plots, you can see that your solution is, you're going to find your solution in those surfaces. Again, this is predefined objectives. So you have, in the end, you have a whole bunch of solutions will satisfy your design objectives. Overall, we look at 25,000 cases over 73 generations. The total computation time is about 5,400 hours. It's long because, again, your ARC code is expensive. So next thing is that, okay, so now we have a whole bunch of solutions, potential solutions along this Pareto front. Next thing is, how do we choose from them? We have many of them, right? So we do this by calculating the weighted distance from the perfect core objective. So you assume that you have there is a core design that gives you the perfect performance, which is not existed, right? But you imagine there is one, and it is over here. So you calculate the weighted distance of each of the individual solutions along this curve to that perfect design, and you rank them by the distance. And of course, how do you assign weights to the different design objectives? It's pure subjective. You can assign all the way to one parameter. You can assign equal weights to different objectives. And so over here, I list the 7 options by using different combination of this weights. And then in the end, we calculate their, we check their performance. The first column is the reference design without optimization, and option 1 or candidate 1 to candidate 7 represent the cases with different weights. The first one is with all the weights, put the plutonium external feed, which is the parameter we're trying to minimize, right? So you can see that over here, you can find a really low value of a plutonium external feed. There's 126 kilogram per year. This lowest among all the cases because you put all the weights to this case. And similarly, you can find the same behavior for option 2 and 3. Option 7 is where we call it more balanced solution, because all those 3 different objectives share the same weight, like a third of the weight equally. So it's more balanced. Okay. And this figure shows it's just a graphical representation of the performance. Again, it's optimal to reference ratio. The black box shows the reference, and for those 5 design objectives, the arrows are showing the directions we want to go. For example, reactivity swing, we should go down. Core power should go down, right? And everything should go down except for the peak fast flux. So there are a few, the takeaway from this is, okay, from the second to the last, everything are going in the right direction, except for the first one. Or the first one, the reactive swing, we want to minimize it, but in the end, we couldn't find any candidate that goes below the reference value or the value associated with the reference design. But it's not a big problem because this reactivity swing is also used as a design constraint. We said we don't want to violate 2,500 PCM of reactivity swing. So as long as those values are below 2,500 PCM, we should be okay. And another takeaway from this comparison is that we didn't really optimize the core volume and and reactivity swing. If you remember that we took this two objects out from the list because based on sensitivity analysis, we say, well, they are highly correlated with the REST3. So which means if we optimize the REST3, we are actually optimizing those two at the same time. And actually, this comparison shows just that. We didn't really optimize those two, but again, we are able to reach a better solution through the optimization. So the issue at this moment we're facing is the direct physics calculation using ARC calculation. Our code system is time consuming. It's 13, 14 minutes. And if you want to go over a lot of function evaluations, it's going to take a long time. So how about we find a reduced order model that can give us a relatively accurate results without taking so much time? So we look for machine learning models to do this. There are a whole bunch of options that you can choose from, but we chose the Gaussian process, which basically is a function. We tend to find the fitting function of the given data, and so that you can really perform a non-physics-based calculation based on the training data. So this is how we did it. We use ARC to start a process, but we don't communicate directly between ARC and the generic algorithm. Basically, we sample the ARC results, and then we generate this Gaussian process model. And we use that to communicate with the generic algorithm and to refine the design. And of course, you have to really check, before you do that, you have to really check the sorry, what's this? You have to really check the accuracy of your surrogate model, right? So this table shows the performance parameters between the surrogate model and the reference ARC solution for different parameters. And most of them are very good, except for this peak burnup and peak pressure drop. We decided it is acceptable because these two are always, based on our calculation, far from the design constraints. These are all design constraints. There's not design objectives. So even though there is about 10% difference, we don't put ourselves in the danger of violating any design constraints. So then we move forward with this surrogate model. It takes about 500 hours to train the surrogate model, and then from then we can use surrogate model to couple with the generic algorithm, perform the optimization. And in the end, we look at 27,000 cases. It takes about 1,100 hours, and we have the same comparison at the end of the calculation, right? And also the same way we have 7 candidates or options. The takeaway here is the performance is very similar to the previous one, except for here. You can see that in some cases, in some designs, the optimized design or solution is not better than the reference one in the plutonium external mass feed. This is because at the end of the surrogate-based optimization, we still use ARC to accurately calculate or evaluate the performance of those chosen designs. Okay, so it means, and during the optimization, the surrogate model told us this values are below the reference value. But as we run ARC and to re-evaluate those performance, we find that it's not the case. They are actually exceeding the reference value. So that shows basically there's discrepancy between the surrogate model, discrepancy of the surrogate model from your physics-based ARC calculation. Okay. We also did something to combine those two approaches, but I don't think we'll have time to go over this. I need to jump to the next topic. So I'll stop here. And so this table shows the comparison of the different options that we looked at. So that's the first part, is how we use sensitivity analysis in the optimization of a sodium liquid fast reactor. One thing you need to pay attention to is really how well you can optimize your design depends on how confident you are with your physics model and your circuit model. If your ARC model is not reliable enough, you won't be able to reach to the good design, right? So that comes to the second topic. How do you increase the how do you validate your model so that you have increased confidence when you perform a study like this? So in the second topic, I'm going to talk about the insertion propagation for this FFTF, which is sodium liquid fast reactor transient test. This again is in collaboration with our Argonne National Lab. So this is in a framework in an International Atomic Agency project, which is designed to provide, support to validation of SFR analysis tools. They use the experimental data from the Fast Flux Test Facility, FFTF, in one of the transient tests. So FFTF is a 400 megawatt sodium liquid fast reactor, which has been fully operated for a good 10 years. So what this test was about is the reactor was operating at 50% the full power, 100% flow, and then all of a sudden they turn off the pump, okay? And you can imagine that the transients start from there. What they want to test is really the capability of this then new design, the gas expansion module, which is used to provide negative feedback so that you can make sure that the reactor can transition to a decay heat power level before violating any safety margins. The way it works is when the pump is off, the sodium level, which was above the core level, the active core elevation in the gas expansion module, will drop, right? And then by doing so, you introduce large leakage to the core so that the reactivity will go down. And that was really crucial to compensate the large Doppler coefficient, which is in the MOX fuel. So that earlier, Argonne did this calculation of the core coupled system calculation to validate their tools. So basically, they perform a two-step calculation. First one is the core neutronics calculation. At the end of the calculation, again, they use diff3D and percent. At the end of the calculation, they come up with the reactivity feedback coefficients. And there are 7 of them, right? And they feed this 7 reactivity feedback coefficients to the system model, which has a point kinetics on the neutronic side. But on the TH side, they use this channel-based numerical model. And those reactivity coefficient can be used in the point kinetics model to predict the power, and then the power will be used in the TH model to predict the temperature, okay? And in the actual test, measurement of the coolant temperature was done in the 2 assemblies circled over here. In addition to the temperature, you also have the power and the reactivity measurement. So what they found is there is fairly good agreement of the net reactivity, but you see there is some deviations in a certain period of time, but there is some problem with the temperature measurement. And then the suspicion at the time is, can we use the uncertainty propagation to understand if the nuclear data uncertainty can be partially responsible for these discrepancies? Because all those calculations are best estimate calculations, where use best estimate data and numerical models together. But there's no uncertainty information being considered. In the previous studies, we have shown that nuclear data uncertainty has a large impact on some of the feedback coefficients. And in turn, we noticed that they will change the value. They have large impact also on the system responses, such as temperature and reactivity. So what we did is we propagated uncertainty from nuclear data through the core calculation, the D3D person, and to generate this correlated feedback coefficient. So you have 7 of them. This is just a representation of that matrix. You have 7 feedback coefficients, and they are correlated in the sense that they can all trace back to the same nuclei and reaction pairs. And once you have this uncertain input parameters for the second step, which is the system transient analysis, you can propagate those through statistical sampling approach and to evaluate the system response, the mean and the standard deviation of the system response. So that's the whole approach of this study. You propagate the uncertainty from nuclear data to feedback coefficients and to system responses. And so this part shows how you actually generate the uncertainty or covariance matrix of the feedback coefficients. I will skip all the details. But what I want to point out is that you have spatial correlations and coefficient correlations between the feedback coefficients. Spatial correlation stems from the fact that you have spatial locations in the core that are coupled together, right? And temperature increase, for example, temperature increase in one region will affect the temperature in the next region. So when you talk about the feedback coefficients, they should not be generated independently. They should be generated in a correlated way. Then you also have this coefficient-wise correlations. This is because many of the reactivity coefficients can be traced back to the same isotope and reaction pair. For example, uranium-238 elastic scattering is found to be important. Sodium scattering cross sections are found important for different feedback coefficients. So naturally, you would think those feedback coefficients are correlated, and so is their uncertainty. So we did first we did a study on the impact of nuclear data uncertainty on different reactivity feedback coefficients. We have 3 global ones, which are used across the entire reactor: the jam, reactor radio expansion, and control driveline feedback. And we have a few, actually 4 of them are considered to be local because these are associated with the local properties, the fuel density, the coolant density, etc. And you can see that among the global reactivity feedback coefficients, the GEM, the gas expansion module, has the largest uncertainty. And the majority of the large uncertainties are coming from the sodium elastic scattering cross sections and iron 56 elastic scatterings. Okay, these are the main contributor to the uncertainty. And what I mentioned earlier is that these coefficients are not only spatially correlated, but also in coefficient-wise, they're dependent on each other. So we perform 4 kind of studies to gradually take away those dependence. The first study, case 1, is, we add dependence to the study. The first one is fully independent, where you only consider the diagonal items in the matrix, in the covariance matrix, which is the yellow one. And the spatial dependence is where we consider the same feedback coefficient, but different spatial zones, which is the orange plus the yellow plus orange. So in orange ones, you consider the same coefficient, but in addition to that, you also consider spatial dependence. And the third case is the yellow one plus the blue region, where you also consider you consider spatial dependence for the same coefficient. In the last case is a fully dependent case where everything is considered. It's the most complicated case. So we then, once we have this coefficient, once we have this covariance matrix, you can sample it through Cholesky decomposition. And I'll skip this details over here, but basically you can sample it many times. You can run different evaluations of the core performance, and then you can collect, at the end of calculation, collect the information and perform statistical analysis. So here is what we got from the fully dependent case, which is case 4. The black curve shows the reactivity feedback from the measurement. And the blue band actually shows the 2 sigma range of the net reactivity predicted by the system code. And you can see it fully covers the measurement data 100%. There was deviation earlier in a certain range, but then by propagating the nuclear data uncertainty, we're able to cover the whole range. And of course, you can see the breakdown of the net reactivity. You have a large negative reactivity from the gas expansion module. You have some positive negativity feedback from the Doppler just because of field temperature decreases. And as you move on to the temperature prediction, which is shown over here, you see the best estimate data results plus uncertainty, which is given blue, works really well for the one of the temperature measurement, which is the second measurement. And the 6th measurement, we still have a large difference. And this is because later on, at the end of the study, we noticed that the heat transfer model in this assembly does not account for the neighboring reflector samples correctly. So that's why you're wrong to begin with. But that uncertainty band added to the best estimate model does cover at the early stage some of the discrepancies observed from the measurement data. And also there is this comparison between the fission power predicted and the measured. Since at the very late stage of the calculation, the uncertainty becomes quite large. So I would say this later part doesn't make too much sense, but we do see some improvement at the early stage of the transient. So we did also some sensitivity analysis on the individual feedback parameters. In this table basically shows the majority of the uncertainty of the responses are coming from the uncertainty of the gas expansion module. That is also, it has a group agreement to what we have speculated at the beginning of the study. This module has a large impact on the uncertainty of the system responses. Okay, I'm gonna stop here and just quickly go over the summary. And we have developed this highly correlated uncertainty to explain the large portion of discrepancies observed between the predicted value and the measurement value in the FFTF loss of flow test. And so moving on, we are going to fill out the covariance matrix with more refined data. And we also want to investigate the impact of the operational conditions and thermophysical properties. Okay, so sorry, I have maybe running a little bit late, but I'll stop here and I'll take any questions you may have. Thank you.
Thank you, Jason. That was really interesting stuff. We have time for perhaps 1 or 2 questions. Any questions from the audience to start with? I'll get us going with a question. You showed a surrogate model for the first of your 2 studies. You showed you ran everything with your genetic algorithm with the PyArc codes.
Yeah. And
then you used a surrogate model. Did you look at if you could now you've got the surrogate model which runs fast, can you run even more cases to sort of really find more optimal cases and push for Pareto fronts, or did you find that the number of samples you had was enough to characterize everything?
Yeah, it's a great question. I think at the time we're more focusing on the balance between the efficiency and accuracy. So we deliberately not going with high number of samples, even though as a follow-up, we should go with higher number of cases to further investigate the performance of certain model. But again, the reason we picked those number is just because the algorithm stopped there as the same predefined criteria are met. But I agree with you, we probably should go beyond that and to see how much more we can improve using the circuit model.
Thanks, Jason. That makes a ton of sense. Thank you. Any questions from anyone else?
I got a quick question, maybe on slide 17. Not sure if that's a valid question, but it's more curious.
Yes.
How does this kind of algorithm was developed? Why is designed this way, and what led to this kind of design of the generic algorithm? Is this from practice, or is this kind of some math behind or some theory behind?
Yeah, so like I said, this whole algorithm is based on the Darwin's natural selection, right, theory. So basically, if you find individuals has a high fitness value, it has more chance to survive and be produced in the next generation. And this algorithm has been widely used actually in the light water reactor optimization. So in the light water reactor world, there's a classic optimization problem of how you can arrange the fuel assembly loading in the core so that it can achieve multiple, sometimes conflicting design objectives. And this genetic algorithm has been widely used for that problem. And so we're borrowing the idea from the light water reactor world to the advanced reactor world. We're testing the applicability of this, and it has shown that it works in this way. But if you ask about rigorous mathematical derivation, I believe there was, but it was from 1970s, if I remember correctly.
I see, yeah. So it's a historically proved working thing.
Yeah, more of that sort, yes.
Great, yeah, thank you.
Okay, we're out of time, but we might be able to sneak in one last question. Okay, perhaps if we wrap it up there then. Thank you again, Jason. You would hear us all clapping enthusiastically were such a thing possible in the modern day and age. We'll invite you up to Wisconsin at some point for some deep fried cheese. It's a real shame we couldn't invite you in person today, but thank you very much.
I really look forward to it. I've been once to the Madison campus. They were really beautiful. I really like the opportunity to come back again.
Look forward to it. Thank you again. Let's all thank our speaker, and we'll wrap it up there.
Okay,
yep, thank you.